Okay, so this is the third and final part of Snell's law, refraction. So I'm just going to label up these diagrams now. This is making a clear point here. So what this is doing is what you were playing around with. We've got the blue boxes here, blue rectangles representing, like for example, glass or perspex prisms. And you're shining light in so that air is the incident. So we've got air and then maybe glass here. And you know, it would be expected that you know that when a ray approaches glass, it will refract and bend towards the normal. The amount it bends depends on the refractive index of the glass. So if you ever get this like an exam question, just bend it towards the normal. A fairly significant amount is quite useful. And what I did ask you to do when you did these experiments is try and observe, do you get reflection? And you should find that at every interface you get partial reflection at the same angle of the incident bounces off in accordance with the law of reflection. And you also get refraction. So this is reflected, this is refracted. And if you increase the angle of incidence, theta I, we keep increasing that angle, then the angle of refraction increases as well, in accordance with, you could work it out using Snell's law. And indeed, the angle of reflection increases. That's what we expect there. So that's the first thing, is fairly, hopefully if you understand there, basically each time we're getting refraction and we're getting partial reflection. You can label all those up if you want to. So the second set, so this is kind of like, if you read this in lines, that first one is just looking at basic refraction. Part B is saying, what if we reverse the direction? We did this with a semicircular prism. We now consider the glass to be the incident, the air to be the refracted. And notice here the diagrams are the same. Instead of the red refracted, it's becoming the black incident at the same angle. The diagrams are identical, and you should find that the emergent ray is the same. It's kind of in other words, you can reverse the direction of light and it follows the exact same path. So if we compare the black and red line here and the black and red line here, they're exactly the same angles, which makes sense in accordance with the equations we looked at, the sine theta I or the sine theta 1, sine theta 2. In fact, it doesn't even matter the direction. The equations don't have direction in them after all. So we should find we can reverse the direction. That's what diagram B is showing us. But we also get some internal reflection. Internal because it's inside the dense medium. So that's again now the reflected. You can see here that my scheme uses green for reflected, red for refracted. And you can label these up appropriately. But what is interesting is if you look at the row A, if we keep increasing the angle of incidence, we can't go further than 90 degrees. And when you're at sort of 89 degrees, you're still going to get a little bit of refraction. There's room to refract. Whereas if you reverse the direction and we're shining the incident in the dense medium, since the angle of refraction is greater than the angle of incidence because the light speeds up, at a certain point we get to a point where we're running out of space to refract, because we get now to sort of like, I don't know, 75 degrees, and we're so close to 90 degrees we can't go any further. And that's actually what happens. And if you kind of go from there down to the next diagram, you can see that if you keep increasing the angle of incidence there up to a certain value, the refracted angle comes out along the boundary at 90 degrees. That angle is the angle of incidence in the dense medium, is called the critical angle. So I'm going to write that down. You can copy this in. If the ray is incident in the slower medium, then theta I can be increased to a point where the ray no longer refracts. You run out of space, it gets to 90 degrees. Okay, and we can say that this occurs at the critical, well, really the critical angle, it sort of refracts at 90 degrees, but the angle where we go along the boundary, that's the critical angle, as I think the diagram explains. So theta c is the critical angle, where we do get refraction, but that's the maximum we can get refraction. And if theta c is above, sorry, if theta incident rather, is above the critical angle, as the next diagram shows, that theta is greater than theta c. This implies we get total internal reflection, no refraction. So yeah, what I said there, really, what I meant to say probably is that at the critical angle you still get refraction, but actually at 90, that's the extreme point. Once you're above the critical angle, you don't get refraction, you get complete reflection. Quick challenge here. You can pause this and have a go if you like. So really, to do this question, you can kind of refer to that diagram. For a material refractive index 1.5, can you determine the critical angle? And all you do is you apply Snell's law to that picture and recognise that we can call the refracted angle 90 degrees. So we're asking for the critical angle theta c. If I apply Snell's law simply, sine theta 1 I'm calling sine theta 2, c. Sine theta 2 is 90 degrees, so it's going to be sine of 90. And that's going to be n air, because the 90 degrees corresponds to the air, so I'm flipping the n's as usual for refractive index Snell's law equations. And we're told that the refractive index for the medium, which is corresponding to that angle, the theta c part there, that's 1.5. And that implies then that theta c is going to be sine minus 1 of sine 90, because n air of course is just 1. So if I rearrange that, I get sine theta c is sine 90, which is also 1, divided by 1.5. And I get for that 41.8 degrees. And indeed, actually, so that's our answer. Then at 41.8 degrees, if we have a material, you can't go above 41.8, it's going to just bounce inside the medium. And you can generalise, it's not given in the IB data booklet, but in general you can say for any material, sine of theta c divided by sine of 90, which is 1, is equal to n air, which is 1, divided by n for the medium. So we get sine theta c is 1 over n. That is, you can find that on the internet. So if you've got a material of refractive index, for example, 1.5, you can figure out the critical angle for that medium. I hope that is useful, and I think it's very important that you work through these problems yourself and make sense of it. Thanks very much.